Hi everyone, this is Manjula, lecturer in electrical, working at GIOE Secunderabad. So today we will see about the DC motors. Objectives of this presentation is that on completion of this period you could able to know Fleming's left-hand rule and the working principle of a DC motor. Fleming's left-hand rule and working principle of a DC motor.
Work.
So DC motor. What is a DC motor? A machine which converts electrical energy into mechanical energy is known as DC motor. So, when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force and tends to rotate. And this force acts in a direction perpendicular to both the direction of the current and the magnetic field. So what does it mean is, whenever a current carrying conductor is placed in any magnetic field, so that current carrying conductor will experience some force which tends to rotate. So by the rotation, so we'll get a mechanical output. And the force which exerted will depending upon the current direction and the magnetic field direction. So the direction of the force is found by Fleming's left-hand rule. So this is the Fleming's left-hand rule. Here the three fingers, thumb, forefinger and the middle finger, placed perpendicular to each other. So the thumb here indicates it is a direction of the motion, direction of the force, and the forefinger is the lines of flux, means the direction of the field, and the middle finger is showing that the direction of the current. So this is a direction of the current which is flowing in a conductor. So hold your left hand with forefinger, middle finger and thumb at right angles to each other. And the forefinger represents the direction of the field, middle finger represents the direction of the current, and the thumb indicates the direction of the force. So as shown in the figure, already I said you. So this is about the Fleming's left-hand rule. Now we'll see the working of a DC motor. So we already know the basic principle around a DC motor, how it will rotate and how it is rotating. So here if you see there are north poles. And the figure 2, this figure is telling that the field set up independently by the main poles and the armature conductors. And this is a combined effect of both the fields. So these are actually a armature effect. So here the field set up independently means by north pole there will be a setup of field. Apart from that, there will be another field setup around the armature because already a conductor which is carrying the current. So there will be a field around that conductor. Okay. So here in these both diagrams, there is a difference that here only the independent field setup is only acting, and here the both field setups, including the actual main field and also the armature field, both are acting. So in this diagram, these arrow marks are showing the direction of the force, and this is the current carrying conductor direction. So here, when the terminals of the DC motors are connected to the DC supply, the field magnets are excited, developing alternate north pole and south pole. The armature conductor carries current. So armature conductors under north pole are assumed to carry the current downwards, which is cross. Okay. So these north pole and south pole have been developed only after when we connect the terminals to the DC motor, means when we give supply to a DC motor. So then north pole and south pole will be developed, and the current is already passing through the armature. It is in such a way that the current carrying the conductor under the north pole is positioning downwards, which is cross. So obviously other end will be the upwards, which is dot. That is armature conductors under the south pole to carry current upwards, that is dot. And the direction of the force on each conductor can be found by applying the Fleming's left hand rule. So the small arrows showing, that is placed above each conductor, shows the above each conductor here shows the direction of the force. And each conductor experiences a force which tends to rotate the armature in anti-clockwise direction. So these forces collectively produces a driving torque which sets the armature to rotate. So here now we understood that each conductor will develop a force, and all the conductors are acting in the same direction. So all the forces collectively tends to rotate the armature. So that is how the motor will rotates. So the mechanical power will be developed in a motor once when we give an electrical input. Fine. I will show you another animated video so that you could able to understand the motor concept clearly.
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, in elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC, via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current in left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current in right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, due to moment of inertia, turn continue to rotates and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is aligned in direction of magnetic field, that is, from north pole to south pole, and second finger is aligned in direction of a current in the left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is aligned in direction of magnetic field, that is, from north pole to south pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near south pole, experience upward mechanical force, and near north pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil.
So hope with this animation you could able to understand better about a DC motor and also Fleming's left hand rule. In the same session, we will see the significance of the back EMF, Previously, we have seen the working principle of a DC motor and the Fleming's left-hand rule. Now, we will see the significance of a back EMF and the back EMF formula. So, what is the significance of back EMF in a motor? We know already that the generator circuit diagram, so the motor circuit diagram will be the direction of some of the current directions will be changed. We will see even the circuit diagram. So here, when field windings of a DC motor is excited and the current IA flows through the armature conductors, a torque is produced. So, when the motor armature rotates, the armature conductor cuts the magnetic flux. So, according to Faraday's laws of electromagnetic induction, EMFs are induced in the armature conductors. Fine. So, this is a motor, we know that it is a motor, and this motor armature conductors are already connected to the electric supply, so the current is flowing through the armature conductors. Here what's happening, though the already carrying current conductor is placed in a magnetic field, it is experiencing some force. Meanwhile, it is also cutting the flux. So according to according to Faraday's laws of electromagnetic induction, there will be the EMF induction in a conductor, which is cutting the flux. So we know that the Faraday's first law is saying that whenever a conductor cuts the magnetic flux, an EMF will be induced in the conductor. So according to that law, so now here the armature conductor is cutting the flux. So EMF will be induced in the armature conductor. This is just like a generator. So see here, this is a motor. So this is a armature motor. So the direction of the induced EMF is in opposition to the applied voltage. So this is an applied voltage. As it is a motor, we will apply the voltage, and the induced EMF will be opposite to the applied voltage. Okay, and which is referred as a back EMF because it is opposite. And the equivalent circuit of an armature is given here. So the armature circuit is equivalent to a source of back EMF EB in series with an armature resistance RA here and put across the DC supply voltage, that is V volts. So the applied voltage V must be large enough to balance both the voltage drop and also the back EMF at all times. So that is V is equals to IA into RA plus EB. Okay, so that is here V is equals to EB plus IA RA, where V is the applied voltage across the armature, EB is the induced EMF in the armature, and IA is the armature current. RA is the armature resistance. So we know that according to the generator principle, the EMF generated value EG, that EG is equals to pi Z and P by 60A. So here also the back EMF EB, we are indicating it as EB. So the value will be same because it is inducing according to the same principle. So the back EMF is induced due to the generator action. The expression of the back EMF EB is equals to pi ZNP by 60A, where pi is a flux per pole in Webers, Z is a number of armature conductors, N is a speed in RPM, P is a number of poles, and A is a number of parallel paths. So here, back EMF depends on the speed. So according to this equation, you can directly tell that EB is depending upon N. So EB will depend upon pi Z N P by 60A. If already designed motor, then I can say that Z number of conductors are fixed, number of poles are fixed, number of parallel paths are fixed, and flux might be varying and N speed might be varying. So I can say that EB is directly proportional to pi into N. So here, so according to that, I can say that back EMF depends on the armature speed. So if the speed is high, the EB is large. Hence, the current is small. So how this current is saying small? That we know that the applied voltage V is equals to EB plus IARA. So from that equation, I can say that IA is equals to V minus EB by RA. So if EB increases, the current IA decreases. So if the speed is low, the back EMF is less. So therefore, the armature current is small. Yes, better I will write that equation. So according to this equation only, applied voltage minus back EMF divided by RA. Okay. So here this line which is saying that if the speed is high, so if EB is high, so this factor will reduce. So hence IA will reduce. So we know already that I can say according to the EB equation that EB is proportional to speed, that is N. So if N increases, EB increases. Okay. So likewise, if the speed decreases, if this factor decreases, overall value increases, so IA increases. So speed decreases, EB decreases. If EB decreases, this increases. So IA increases. So EB acts like a governor. That is, it makes a motor regulating so that it draws as much current as just required. So here the significance of back EMF is that EB is acting like a governor. So how much armature current actually it requires, only that part of the armature current it is taking. Okay, so that is the main significance of the back EMF, which is very important. So by this session, hope you are understood about the DC motor principle the Fleming's left-hand rule, and the actual significance of the back EMF, and also the back EMF formula. Hope in this session all the topics you understood, and thank you.